Welcome to the chemistry lecture series. And under electrochemical corrosion, today's topic is types of electrochemical corrosion. In my previous lectures on the electrochemical corrosion, I have explained how the corrosion takes place, what are the causes of corrosion, and what are the factors that affects the rate of corrosion. So in today's lecture, we'll discuss about the types of electrochemical corrosion. We can classify electrochemical corrosion into 4 types. First, differential metal corrosion. Second, differential aeration corrosion. Third, stress corrosion. And fourth, grain boundary corrosion. The differential aeration corrosion can be further subdivided into waterline, pitting and crevice corrosion. But before going to the types of corrosion, let us first understand the galvanic series. It's that series in which the metals and their alloys are arranged on the basis of their relative oxidation potential in the seawater. So one can question that if the electrochemical series already exists, then what is the need of another series? So the answer to this question is, there are certain metals whose corrosion behavior cannot be explained with the help of electrochemical series, such as corrosion of aluminium and zinc, silver and titanium. Zinc and silver are below aluminium and titanium respectively in the electrochemical series. Still, zinc and silver corrodes faster than aluminium and titanium. But this answer can be get by the galvanic series. So, a series which gives us the answers about the corrosion behavior of the metals is called the galvanic series. And this series is prepared after a careful and extensive study of the corrosion behavior of the metals and alloys in an environment resembling seawater or the natural environment. So we can differentiate the electrochemical series with the galvanic series. In the electrochemical series, the metals are placed in the fixed positions, whereas in the galvanic series, the position of the metals varies. The electrochemical series predicts the displacement tendencies of the metals and nonmetals when they are kept in the 1 molar electrolyte of the same metal, whereas the galvanic series predicts the corrosion tendencies of the metals and nonmetals in the actual environment. The electrochemical series comprises of metals and nonmetals, whereas the galvanic series includes metals and their alloys. The electrode potential E0 in the electrochemical series is determined using SHE, standard hydrogen electrode, whereas the same is determined using the caramel electrode in the galvanic series. There is no information available about the alloys of the metals in the electrochemical series, whereas the galvanic series shows the corrosion behavior in detail about the alloys along with their metals. Now let us start with the different types of electrochemical corrosion. The first one is the differential metal corrosion. When two different metals are in contact, the one with lower reduction potential becomes anode and starts suffering the corrosion. This can be explained nicely with the help of metals such as iron in contact with different metals such as copper, tin, zinc and magnesium. We all know that the reduction potential of iron is minus 0.44 volts. And when this iron is in contact with copper, which will become the anode? Obviously, iron will become the anode and starts getting corroded. Similarly, if the iron is in contact with tin, the tin is having a high reduction potential compared to iron. Therefore, again iron will form the anode and starts corroding. But when the same iron is in contact with zinc, which will form the anode? It is the zinc which forms the anode and not the iron, because the reduction potential of zinc is minus 0.76 volts, and therefore it will form the anode and starts getting corroded. Magnesium and iron, if they are in contact, the magnesium will form the anode and not the iron, and it is the magnesium which will suffer corrosion and not the iron. Now let us take the example of zinc and copper. So which one is having a lower reduction potential? It is the zinc, and therefore zinc will suffer corrosion when it is in contact with copper. So the reduction potential plays an important role in determining the rate of corrosion. And this type of corrosion is called differential metal corrosion. Second type of corrosion is the differential aeration corrosion. When a metal surface is exposed to air, the portion of the metal surface which is less exposed to the air forms the anode, and the portion of the metal which is exposed to more air forms the cathode. And we all know that it is the anode which suffers the corrosion. So let us take the example of an iron rod immersed half or partially in the salt water. This can be explained with the help of this figure, where the iron rod is kept in salt water. The portion of the rod which is exposed to the air forms the cathode, and the portion of the rod which is immersed in the salt water forms the anode and starts getting corroded near the bottom of the rod by the loss of electrons. Differential aeration corrosion, as already said, is further subdivided into three types: waterline, pitting and crevice corrosion. The waterline corrosion is often seen in the partially or half-filled iron tanks, in the ocean-going ships, on the ship hulls. Pitting corrosion is seen in the cross wires in the iron fencing, or the boxes which have dust deposited on their surface. It can also be seen on the metals which have welded parts, or there are joints on the metal. So these type of corrosion are called waterline, pitting and crevice corrosion. Let us first start with the waterline corrosion. The waterline corrosion is often seen in half or partially filled steel tanks. Now we can see here, this is an iron tank in which the water is filled partially in the tank. So the part of the tank which is exposed to the air just above the waterline, this is the waterline, and the part which is more exposed to the air forms the cathode. Whereas the part just below the waterline, near the waterline, just below it, forms the anode and starts suffering corrosion due to the redox reactions taking place. And the formation of rust, Fe2O3 3H2O, is seen deposited here near the waterline. So it is called waterline corrosion. The pitting corrosion is again a type of differential aeration corrosion, and maybe due to the area which is less exposed to the air, and this is seen in the cross fencing, in the cross wires, or if the surface of the metal has dust deposited on its surface. So we can see here in the figures where the two wires are crossing each other, and the portion just between the two wires forms the anode because it is less exposed to the air compared to this entire portion here and this entire portion which forms the cathode. And similarly, this metal surface, this is the dust which is deposited here, and the region below the dust forms the anode. Now this large cathode demands more electrons from this small anode, and it results into the formation of holes. This is called pitting corrosion, and it's very intense. The crevice corrosion is another type of differential aeration corrosion where the metallic objects are joined with the help of nuts and bolts. So we can see here the two metals are joined with the help of nuts and bolts. So the portion which is less exposed to the air forms the anode, and this bigger portion forms the cathode as it is more exposed to the air, and it leads to intense corrosion. This type of corrosion is called crevice corrosion. The third type of corrosion is the stress corrosion, and it is due to the stress in the metal surface. The portion of the metal which is under stress forms the anode due to the slight displacement of the atoms on this portion. So we can take the example of a forceps. Now this forceps here, this is the portion which is under stress and it forms the anode and suffers the corrosion. The fourth type of corrosion is grain boundary or the inter-granular corrosion, and is generally found in the alloys. Now stainless steel is the best example of any alloy, which is a mixture of iron, carbon and chromium. In the grains, the carbon and chromium are present, but the chromium and carbon combines to form chromium carbide, which gets precipitated at the boundaries, and the concentration of chromium adjacent to the boundaries becomes less, resulting into the formation of anode, and thus it starts suffering the corrosion. So this type of corrosion can be prevented by using low carbon content in the alloys or by proper heating of the alloy so that the chromium and carbon dissolves back into the alloy. There is one more special kind of corrosion that is called the microbial corrosion, which is due to the various microorganisms present in the nature, whether it is soil, air or water. These microorganisms can survive in the presence of air, that is called aerobic, and in the absence of air, that is called anaerobic. So they can be classified as aerobic or anaerobic bacteria. The aerobic bacteria, if they are present in the soil, they consume the oxygen present in the soil and decreases the concentration of oxygen there. And if in such a soil a structure is erected, then it suffers from differential aeration corrosion. Iron and manganese are such bacteria which forms the differential aeration couples, and they destroy the structures present in such a soil where they are present. Similarly, the anaerobic bacteria such as Microspira or Vibrio desulfuricus, they reduce the sulfates to sulfur to prepare the protoplasm. And when these bacteria die, they release hydrogen sulfide. Now this is an acidic gas, and it converts the iron into ferrous sulfide, which is a corrosion product. This type of corrosion is usually observed in the cast iron, where in the anaerobic condition the corrosion is very intense and it is a localized type of corrosion, leading to the formation of pits and blockages in the pipes. The other bacteria which lives in the cooling tower, such as Flavobacterium and mucoids, they make the surfaces slimy, and the concentration due to these bacteria becomes very less, leading to intense corrosion. So the microbial corrosion cannot be ignored. It is very, very important to learn about this. So we can conclude that we know that corrosion is an inevitable process. But if we know the types of corrosion and the factors that affects the rate of corrosion, corrosion can be slowed down. And by taking special measures, we can increase the lifespan of many metals to a great extent.